I can put it on my YouTube channel, so whoever was busy and couldn't attend this session, he would be able to join with us, or sorry, you can watch it later on the YouTube. Give me just one last time. I will just adjust something in the options so I can let people in as well. And let's close that one. Save. Yes, I will give you my YouTube channel. Sure, I will send the YouTube channel. Okay. Nope. Very good. Okay. Hello, everyone. My name is Salah Ataya. I'm a condition monitoring specialist, certified level 4 in vibration analysis, and level 3 in thermal imaging, level 2 in oil analysis, certified maintenance and reliability professional, and have ARB certification as well, engineering degree in mechanical engineering since 2007. And I'm living in Australia for almost about, sorry, not now, not that one. This is for next session. I'm living in Australia for almost 12, 13 years now. And I have my own company. I have two companies, one called MCS, Machinery Consultation and Services, which is the company for the machinery consultation. And I have 4 guys work with me in the team at the moment. And also I have another company called MDI, or Machinery Diagnostics Institute, which is the company for the training. MDI is a training institute. We training partner with Mobius Institute, with ICML for lubrication, with infraspection for thermal imaging, and we have our own turbomachinery courses, which is turbomachinery analysis, the advanced turbomachinery analysis, the advanced machinery balancing, and turbomachinery data collection. This is the course package we introducing. We plan to make this free workshop sessions to talk about several topics in the condition monitoring. We will start with vibration analysis. We're going to talk about, like, it will be one session every month, short session, but it's effective. I'm pretty sure you will like it. We're going to talk about the turbo machine, the vibration analysis, data collection, the vibration analysis, the fault analysis, how to make vibration analysis report, about thermal imaging, about oil analysis, about on-site balancing, laser alignment, and asset reliability. Many topics over this year, and it will be one session every month. And at the end of the session, during the whole session, it will be recorded, so we put it in the YouTube channel so everyone can see it later if he couldn't attend the session. Okay, let's start. We're now going to talk about the vibration measurement sensors and data collection. We have different measurement sensor types. We have the accelerometers, and these accelerometers are used in measuring casing absolute vibration. And with accelerometers, don't have moving parts. You have long life sensor. It have different sensitivity, 100 millivolt per G, and this is the most common one used in the data collection, and 500 millivolt per G, which is the one have higher sensitivity, and that the one we use in special cases when we trying to take some vibration data on low speed machines. Those sensors require calibration, but mostly now no one calibrate those sensors. When they get old, within 3 to 5 years, you replace it with a new one. Calibration would be expensive, and the replacing the sensor is much cheaper now. Reading of this sensor is affected by mounting type, and we have frequency response between 900 to 600 CBM. Those accelerometer measuring high frequency vibration, you can have flat or 2-pole base magnet, single and tri-ax accelerometer. External power is required for accelerometer, not like the transducer. You have temperature limited to 250 Fahrenheit, easy to attach for routine vibration data collection. Reading can be integrated to velocity and double integrated to displacement. And the units for this one, a participant has said the caption line. Okay, very good. 1 second. Could you remind me? Is caption and English. Good. Save. Can you see the captions now? I believe you should be able to see it in English. Yep. If you want to, okay. You should be able to see the caption now, like it was supposed to appear here. I don't know what happened to the Zoom today. some features is not. Yes, show caption. Yes. Now you can see it. So you can now, everyone can see the caption. If yes, give me thumbs up. That would make it easier. Perfect. And we have many mounting methods when we're trying to take some vibration data using those proximity probes. No voice. Someone saying no voice. Everyone can hear me or you cannot hear me? Could you please let me know? If you can hear me, please type on the chat that you can hear. Yes, we can hear. Very good. Thanks, Ahmed. Very good. Very good. Excellent. Excellent. Thank you very much. So you have the probe tip, which is the handheld, and you have frequency response range between 250 to 700. You have the two-ball magnet, and this one is specially used for the curved surface. And you have direct stud, and this is permanently mounted sensor. Especially it can be used with machines you cannot reach easily by the routine data collection. Osama, will this session will be recorded? Yes, Osama, and it will be in the YouTube channel. Flat magnet with the flat surface. You can not use the flat magnet with the curved surface. Sabuddin Khan, he say, dear sir, no voice in this meeting. Yes, there is voice. Everyone can hear it. I'm not sure why you cannot hear this one. If anyone else cannot hear, please let me know. Muhammad, he can hear it. Please, if you cannot hear, check out, like log out and log in again, okay? And you have the adhesive mounting. With adhesive mounting, you have the frequency response is higher between 8,000 to 16,000 hertz. So with different mounting type, you will get different response ranges. Ahmed Ibrahim say, Khan use computer audio. I have here, I'm using the headset for the microphone and for the speaker, and I believe the sound is clear for everyone. If there is any problem with the sound, please let me know in the chat. And we have here, this is casing for steam turbine. We still can, for any questions, because I will not be able, because we have now about 29 participants, so I will not be able to answer all the questions because it's a small session, but all the questions will be recorded on the chat. So I have the chat recorded. So if anyone have a question, please put your email after the question. So I can answer, I can email you the answer for this question, okay? So you have here, this is the steam turbine casing, and as you can see, you have the accelerometer on the casing. So you can collect vibration data from the casing of bearings using those accelerometers. You have the velocity transducer. This is the second type of vibration sensors. And this can measure the casing absolute vibration. It contains moving parts. As you can see, there is a spring and coil and magnet. No external power is required because the movement of the coil inside the magnet by itself, it will generate the power required to be converted later on from analog to digital reading so you can get the vibration data. It has short lifetime because of the mechanical parts inside the sensor. Temperature limited to less than 250 Fahrenheit. Frequency response range between 900 to 90,000 CBM. Reading can be integrated to displacement from the velocity. The third type of sensors we have is the proximity probe. Proximity probes or proximity transducers or non-contact eddy current. It use a radio frequency electromagnetic field to measure the distance between the non-contacting probe tip and the observed target. Measuring shaft position within the clearance of fluid film bearing, and you get DC voltage. And measuring the shaft vibration amplitude by AC voltage. So with proximity probe, you get two types of voltage, AC and DC. DC will tell you the shaft position inside, for example, the journal bearing, or for the axial movement. And the AC will give you the shaft dynamic vibration in microns or mils peak to peak. And mostly it's used in steam turbine, gas turbine, any machine with journal bearing. It doesn't have moving parts. You have sensor sensitivity about 200 millivolt per G or 7.87 volt per millimeter. And this is the sensitivity for the sensors especially used in measuring vibration data. Those sensitivity can be different with different sensor type, and you'll have different linear ranges as well. And it can have several applications, like it can be used in measuring the eccentricity, it can measure the speed, it can measure the differential expansion. So those sensors have different sensitivities with different sizes, with different linear ranges, and it can be used in different applications on turbine. But here, which is the most common one we're talking about, is the 200 millivolt per mil or 7.87 volt per millimeter. This is the one which is used in radial vibration data collection. If you got negative voltage detected, this is the normal voltage you can detect from the proximity probes. If no voltage or positive voltage, shaft, this will mean there is something wrong, and shaft material will be affected by the probe sensitivity. As I mentioned, those proximity probe will give you DC and the AC voltage data, and the DC voltage gap is directly proportional to the gap or the distance between the probe tip and the shaft surface. When you have larger distance between the probe tip and the shaft surface, this means you have lower voltage value. And when the shaft is more close, like have a smaller gap, this means you have higher voltage value. So if you look here from this plot, you have 2, 4, 6, 8, 10, 12. This is the voltage value. Remember that the output voltage value was minus DC. So which number is bigger, minus 2 or minus 24? Definitely minus 2 is larger than minus 24. So when you have minus 2, this means you have larger voltage value and the gap is smaller. When you have when you have lower voltage value, this means you have higher gap. And this is almost the midpoint here, around 10, the midpoint of the linear range. The linear range for proximity probe at 7.87 volt per millimeter as sensitivity is between minus 2 to minus 18, minus 20. That's why when you gap the proximity probe, you put it around between minus 8 to minus 10 or minus 11. This is the midpoint of the linear range. So you can ensure that when the shaft is moving further or away from the probe or near to the probe, you will still be in the linear range of the proximity probe. As you can see here in this one, when the rotor start to be away from the proximity probe, you will get the lowest voltage value and the biggest shaft gap. And here you will get the highest voltage value and the smallest shaft gap. This is proximity probes, and this is what we call internal mounting. There is two types of mounting. There is internal mounting and external mounting. These two proximity probes are mounted internally over the shaft for a steam turbine. Prior to talking to vibration measurement, we need to understand why we are going to measure, what we are going to measure, and how we are going to measure it. Why? What information we are trying to find, and what the appropriate data acquisition parameter, and what sensor we use, and how do we mount it, and where do we mount, and why we collect vibration data in horizontal, vertical, and axial. Many times when I ask in the training courses I'm delivering that, what is the reason we're measuring horizontal, vertical, axial? And then I got the answer, because when you measure in horizontal or vertical and axial, you will be able to detect different type of faults. Some faults we see it in horizontal, some faults we see it in vertical, some faults it give more, it will be more, let's say, like appear with higher level or more dominance in this direction. But this is not the right answer. Like, we're not measuring in 3 directions because the different faults appears in the different directions. The reason we're measuring in different direction on the machine, because the machine response is different between horizontal and vertical and axial, because the stiffness is different between horizontal and the vertical and axial. That's why we have imbalance with higher amplitude in the horizontal direction for most of the machines, because the response we get on the horizontal direction is higher than what we get from the vertical direction. Why is that? Because if you have the vibration and the stiffness is equal the load per unit the deflection. So if you apply some load on the horizontal direction on the motor, it will deflect easier than you apply this load on the vertical. In the vertical, you have, for example, the concrete, the ground, it's much more solid. Imagine you have a soft drink can. and you try to push it from the horizontal side, it will easy move. But if you try to put your leg and press on it vertically, it will take more time because it will resist, because the stiffness in the vertical higher than the stiffness in the horizontal. That's why the response of the vibration in horizontal will be different from the response of vibration in the vertical. So if you have vibration response equal the force divided by the stiffness. So if you have, for example, force coming from the machine and you have high stiffness, the response will be lower. And if you have lower stiffness, the response will be higher. So the force is the same. You have, for example, unbalance. The unbalance will give you higher vibration in the horizontal direction because the stiffness will be lower, so the vibration response will be higher. But in the vertical, you have higher stiffness, so the response for the vibration will be lower. That's why we measure in different directions to be able to see the machine response on the different directions. If you have like motor and fan here, we need to know where we make these measurements. Like, for example, this is point 1, 2, 3, and 4. So you can name them 1, 2, 3, and 4. However, if you use this method, you must use machine layout in your report. So if you say, I have a vibration problem in bearing number 2, if I don't know that this bearing number 2 is the drive end bearing of the motor, I will not be able to understand what is the problem. But you can use this method, but you must put the machine photo. I don't like to use it because it's not easy. And every time you will try to use it in any report, you will have to put a photo and you have to mark all the points. So that more work you have to do to be able to reach to this result. However, you can name it MNDE or MDE, FDE or FNDE, motor non-drive end, motor drive end, fan drive end, and fan non-drive end. So this is a fan. You have the motor, coupling, and 2 bearings for the fan. This is the motor drive end. So if I told you I have, there is a bearing fault in the motor drive end, so you'll understand that I'm talking about this bearing. But if I told you bearing number 2, bearing number 3 without a drawing, you will not understand what I mean. So you can name it motor non-drive end, motor drive end, fan drive end, and the fan non-drive end. This is the motor and this is your fan. Also, you can have another way to name it. You can name it motor outboard bearing, motor inboard bearing, fan inboard bearing, or fan outboard bearing. So also this is a good way or terminology you can name your machine with. And this will enable you to understand. If I told you there is a problem in the drive end or the non-drive end, you will understand what I'm talking about. Give me 1 second, take one more screenshot. Sorry, guys. And 1, 2, 6. Okay. So also for the point of the measurement, you cannot just measure at any location. Like if you measure here in the cooling fan casing, that will give you false reading. It is hollow from inside. If you measure here on the base, you cannot measure on the base. You cannot measure on the casing of the pump or the volute. You cannot measure here. You cannot measure on the cover, this cover from rain. You cannot measure on the cooling fan cover. You cannot measure on the base. Where to measure? If you have here motor and pump, this is the best point you can. Horizontal, vertical. You don't have axial axis here. Horizontal, vertical. You don't have axial here. Horizontal, vertical. Yes, you can get axial on that one. Horizontal for the non-drive end and drive end. And this is 2 horizontal and vertical for the pump. You can, if you can put your sensor somewhere in the motor base here, on the motor feet here, you can take some reading. If you can, sometimes if you can have side exit, you can put it here, but be careful if there is any rotating parts. If you have motor and gearbox like what we have in steel mill, in steel factories, horizontal, vertical, you don't have a place for axial here. Horizontal, vertical, you can get some axial. In this gearbox bearing, you can get axial with the axis, horizontal and the vertical, and be careful with the naming of the measurements. You can name this one for example, vertical and this horizontal and this is axial, whatever. But with gearboxes especially, and for vertical machine, as we're going to talk about, be careful. If you name this one axial because it is with the axis, and this horizontal direction and this vertical direction, keep them the same. As well, axial, vertical. You don't have horizontal here. Some people, you can put it here on this bracket. At least you will not get perfect measurement, but you will get good indication. So at least you will know how the machine is behaving at this horizontal direction. And here is, this is your vertical. Also, this is your axial measurement, horizontal, 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 and this is 3 vertical measurements. For vertical machine, you can name this direction horizontal and this one vertical. Also horizontal and vertical. Or you can swap them, make this one horizontal and this one vertical. However, if you decided to make this one horizontal at this direction all the time, so you must keep it horizontal all the time. And if you want to keep this one vertical, you must keep it vertical all the time. So you'll see the effect of the vibration. It will be consistent with every measurement. Some people with vertical machines, they can take the horizontal direction with the direction of the piping. And this will be your horizontal direction. And 90 degree for that one will be your vertical direction. Doesn't matter. The most important thing with vertical machine, if you decide to take one direction and name it horizontal or vertical, keep it horizontal or vertical every time you do the measurement. This is belt-driven machine. You can have horizontal, horizontal, vertical. This is your motor. You have belt, and then you have the blower. And this is the horizontal measurement, vertical. The axial direction, it can be taken here, like at this point. If you take some axial measurement here, that will not be wrong. It will be valid. At least you get something. So this is something you can take. For vertical machine, horizontal and the vertical is not clear. This is your horizontal direction, vertical direction, horizontal and the vertical. If you choose to keep this one horizontal, keep it horizontal with every time you take the measurement. And if you choose to this direction to be your vertical, keep it vertical every time you take the measurement. You cannot swap them. You cannot measure here this time and name it in your software horizontal and this one name it vertical. If you keep this direction of measurement horizontal, keep it like this. Even you can mark it. You can put mounting pads, and this mounting pads have the direction stamped on it, so you will not get confused. As you can see here, this is a couple of bumps. I tried to put many types of machines so I can give you the feeling you have on site. Like horizontal, vertical, horizontal, vertical. If you have side exit sensor and you can squeeze this one to put it somewhere here, that's not bad, can be done. If you can have side exit sensor to squeeze it here for axial, that's not bad. If you have side exit to put it here to get your axial, okay, better than nothing. And you see, get your axial, horizontal, vertical. If you can squeeze something here, okay, that's fine. So you can get this measurement. As you can see here also, horizontal, vertical direction, vertical, this is your axial, horizontal, vertical, this is for pump. This is motor, direct coupled with a small gearbox, coupling, and this is hydraulic pump. With this small motor, you can take horizontal, vertical for the non-drive, horizontal and vertical for the drive. However, because this motor is small, you don't need to take measurement for both bearing. One measurement would be fine, would be enough, because the motor size is too small. If you have a small motor, you don't need to take reading in in non-drive end and the drive end. Okay. This is again vertical machine. You can name those direction horizontal because it is with the line of the flow. This is the pipe flow. You can take this horizontal and name this one vertical. That's what most of the most common. They do the measurement this way. However, if the small motor, we're not talking about the small motor by kilowatt, we're talking about the small motor by distance. Like if the total length of the motor less than 70 centimeters, like this one, less than 70 centimeters, so one measurement would be fine. But if it is long motor, like for example, that one, this is longer one, you need to take horizontal, sorry, you take the non-drive end and the drive end. It's not about how many kilowatt the motor, it's about how lengthy is the motor, how long it is. So if we choose this is as your horizontal and this is the vertical, keep them horizontal and vertical every time. As you see, with this motor, you cannot take only on the middle, for example, because this is long motor. So it have longer length. So you need to take in the non-drive end and in the drive end. This is the fan drive end, and this is the fan non-drive end, and this is a center hung fan. Again, with this one, horizontal, vertical, horizontal, vertical. If I don't have access here to axial measurement, I will not be able to take it. With this pump, horizontal, horizontal, to vertical, and this is your axial measurement. If you want to take axial measurement for the non-drive end and you put your sensor here, that's not bad. You can do it. At least it will give you an indication. This is FD fan. This is very large motor. So this is the non-drive end, the drive end, and the fan drive end. And you don't have access to the fan non-drive end. So you will not be able to measure it. Again, you will take the direction, the measurement at the 3 directions. With this pump, you can take the axial from here. It will not be bad. Give you an indication, better than nothing. And this is your drive end. How do you determine the best vibration monitoring interval so as not to miss catching potential issues earlier to initiate maintenance? Very good question, Martin, but this is not about this lecture. This is the last one about the asset reliability. But short answer and easy answer about you must do criticality risk assessment. And based on the criticality risk assessment for your equipment, you will be able to choose the frequency of the measurement. How this equipment will affect the plant at the production, the environment, the human factor, the breakdown, the secondary damage, the spare part or inventory you have. There is many factors, and then you can rank this with numbers. And if it got high number, for example, I'm trying to explain it quickly. If it will give you like high number or high value, high ranking value, okay, so this it must have like lower frequency for the measurement. But if it doesn't have effect on the environment, on the production, have less effect in the spare parts, it's a small motor, not expensive. At some cases, you can just run it to failure because it doesn't work that you waste your time and take some measurement on this machine. As you can see here, horizontal, vertical, horizontal, vertical. Some motors, by the way, some motors are not from steel. Your magnet will not be able to stick to the casing. So what you do, hold it with your hand. Hold it as strong as you can. Don't be don't make things very complex. If you cannot take it, don't say, okay, the sensor is not sticking, the magnet's not sticking. So try to put your hand strong. And what to do else? Try to get mounting pads and stick them with glue or adhesive or 2-in-1 material to stick on your motor. Then the next measurement, you will be able to get a good and reliable vibration data. And the most important thing is the repeatability and consistent for the measurement. In case a vibration sensor is faulty, what other protection can help trip the machine to prevent a breakdown? If the vibration sensor is faulty, you cannot run the machine with faulty vibration sensor. It must be replaced. And especially if you have steam turbines or a gas turbine or high-speed machines running with proximity probes and they are faulty, it's not safe at all to run it without vibration protection system. You need to have protection system for this machine. I've been once before to collect some vibration data on an old steam turbine. It doesn't have proximity probes and it doesn't have a protection system. They have one guy have vibration data collector, collect vibration data on this turbine between time to time only from the casing. And we got severe damage on this machine. Then I went to the site and I installed a proper proximity probe system for the turbine and been connected to a junction box so we can take the data from BNC, and we put protection system and it's been connected to the DCS so we can trend. So there is no middle answer for this situations. You must have a good protection system to your machine. You cannot say I will depend only on temperature. No. For diesel engines, like this is a diesel engine for firefighting pump, and you can do the measurement at this direction, and this is the pump, horizontal, horizontal, vertical, and vertical. This is ID fan. You have the motor non-drive end, motor drive end, the fan drive end, and the fan non-drive end from the other side, and we will take vibration on the 3 directions. Let's have a look here. Let's have a look on that one. This is a motor driving air extraction pump. With this video, I will show you how you do or how you take the vibration measurement. This is the non-drive end side of the motor, and this is the drive end side of the motor. This is the drive end side. This is the pump drive end, and the other one is the pump drive end, and this is your coupling. Do we need 3 sensors for triaxial? No, just one sensor, which we call triax accelerometer. So here you have your vibration sensor, and you will go to the machine. You will try to put the sensor with the magnet on the non-drive end, and then you will open your analyzer. You're trying to find the route, which is the route for the machine you're going to measure. You will have different routes in your data collector. You will check the machine name that you're measuring the right machine. You will check if the machine is running or not. So I check from the back, this machine is not running, so I will not take measurement for this one, and I will go for the next one. And then when you put the sensor, try to put it gently. In the first time I put it a bit hard, that's wrong. You try to roll it on and put it carefully so you will not cause damage to your sensor, and you will not have a ski slope in the measurement. You will choose the machine, and then you will start to collect the vibration data. You will see, for example, the last survey, what was the vibration levels on the last measurement has been taken. You will click enter, and then you will start to collect the vibration data. Let's have a look. And then you will say overwrite the last one. I will tell him, for example, okay. Then it will start to acquire the vibration data, and then it will be recorded. I take the horizontal measurement, and then after it's been collected, we will go for the next direction. It can go automatically, or you can change this one by hand. Then you will go for, this is, for example, the axial, or you can take it from here. This will be your axial measurement, or you can take it from here. If you don't have a good axial direction, you try to find the best or the easiest solution. Not say, no, I will not take it. If you, at least you get some indication. And now we get the axial measurement. Like, don't say, I don't have measurement direction. No, you try to take the measurement if you can. And then you see here, when I put it, I roll it on. Like I put the side of the magnet ball first, and then I roll it on the next ball. And as you can see here, this is the measurement for the drive end of the motor. You will collect the data, and then you will get horizontal, vertical. Here I don't have axial. You see, I don't have axial, so I will not take axial measurement on this side. And then I'll go for the next one, take the horizontal measurement, and if I can have the vertical, I will take the vertical measurement, and again I will roll it on. And as you can see, this is curved surface, and because it's curved surface, and you see horizontal, vertical, and axial, so I will take 3 measurements. Let's have a look here. This is for vertical machines. As you see, this is the line of the flow. So we can say that this here, this is your horizontal direction, which is the direction with the flow. And we will name this in our software or database as the horizontal direction. So with this vertical machines, you see, we can say this is the vertical because it's 90-degree perpendicular to the direction of the flow on the pipes. So this will be your vertical direction. And this one will be your horizontal direction because it's in line with the pipe. So you can name it this way. And here, if you're going to take some measurement, for example, on motor and gearbox. Yep, this is your motor. And You have the coupling here, and you have the gearbox. So we'd like to take vibration measurement on that one. The motor, we know it, and the gearbox, you need to, of course, be careful about the rotating parts and the guards. This is the conveyor to transfer coal in power station, and this is again the motor coupling. So this is your vertical. You see, I put it over the fence. Sometimes the sensor will be a bit loose. If it is loose, try to hold it with your hand. The best way, if you have a mounting pad which is already stick to the machine casing, but if you don't have, don't say I will not measure it. I don't have axle. At least I will take some indication from here. Will be the horizontal for the drive end. It will give you some indication. And this will be your vertical direction. Okay. If you don't have axial direction here, sometimes you can put the sensor like this. If you don't have a way at all, you put the sensor by the side. This will give you reading. Here, this one in the middle. At least you get something. Okay. But you need to always, when you take some vibration measurement, you need to have a notebook with you. You can write if there is leak, if there is noise, if there is high temperature, if the axle or some measurement has been taken with a special way. Now you go for the gearbox. You can get the drive end in the horizontal direction from here. And then you have the low speed, the intermediate, the output, and you can name all those points here as the input or high, high speed input, high speed output, intermediate speed input, intermediate speed output from the other side, output speed input, the output speed, the low speed input and the low speed output. So you can name it with the different speeds, like high speed input, high speed output, intermediate speed input, intermediate speed output, low speed input, and low speed output. And this is the low speed from the input, vertical, the horizontal direction, as much as you can to collect those vibration data. In some situations, like as you can see in this machine, it's very high. You don't have access to that machine. In this case, you see, you must have permanent accelerometers mounted on your motor and your gearbox. And you have a junction box, as you can see here, with BNC connection to collect this vibration data. So this sensor will be permanently mounted on your machine, especially also for cooling towers. You cannot have access, it's not safe, so you can put it on the gearboxes, and then you can collect the vibration data from the junction box through the BNC connection. The sensor, you can put it in this position, that's okay. This is okay. You cannot put it inclined like this. That should be fine. You cannot put your sensor like flat magnet on the curved. It's not okay to have too many paint layers. It's not okay to have the cable very squeezed like this. That should be fine. When you put the sensor, roll it on. Don't hit the sensor over the surface. In the curved surface, if you use flat, you see, the sensor will be loose. 2-pole magnet for curved surface. And you can have a stud over the curved surface. That should be fine. Measurement frequency range. You can have measurement frequency range like for shaft running speed. This is when you choose the frequency range for the measurement. It could be up to 10 times the running speed. If you have gearbox, you need to see 3 gear meshing frequencies. If you have rolling element bearing, if you can calculate the inner raised effect frequency, multiply this by 10, pump 3 VIN bus frequency, motor 3 times the twice time frequency, fan 3 times the blade bus frequency, and the sleeve bearing 10 times the RPM. We're going to talk about this more in detail next month when we start to talk about the fault analysis. There is many causes for fault signal, like faulty sensor, faulty cable. Very high vibration will cause sensor saturation, poor connection, some thermal transient and vibration transient, and you will see ski slope in your vibration spectrum. That's all for today. Thank you so much, everyone. It was a quick session about the data collection and what you need to do with it. The whole video will be recorded and it will be uploaded to the YouTube channel. And I will send you all email with the next session next month. And if by the end of the month, if I found like not too many people got the email, I didn't get response, I put the link on the as a post on LinkedIn. And also after this the coming session will be finished, I will upload the session to the YouTube channel. I hope you like it. I hope it was quick and I didn't make you bored. The name of the YouTube channel, let me have a look. 1 second. 1 second. I will send the link for the YouTube channel now. And the chat. And done. I put the link for the YouTube channel. Thanks, Ahmed. Thanks for attending. Thanks, Musab. Thank you very much, everyone. I'm trying to make the sessions not too long because I know everyone is busy and people get bored easily. And I'm trying to make it more practical. That's why I put lots of photos. Because, like, I know most of you who attended this, you know what I'm talking about. But what we're really missing is to see too many machines, to feel the what we're doing is more practical. And that's what you're gonna see in all the sessions. Like you will see many photos. We're gonna talk about them more in detail about the situation, what is happening on site, how to act when you see different situation in different machine. In machine, this sensor are not always mounted. You mean the permanent sensor? Yes, the permanent sensor is not mounted at all. You have all the time, you should have your magnet for routine data collection. But for permanent sensors, this is only used, the permanent sensors, if the machine you cannot reach. If you cannot reach the machine, it's in cooling tower or in high location, you cannot reach it. That's why we use the permanent sensor. Thank you so much, everyone. I'm very glad that you attended, and we have good amount of participants, so that's very cool. And we'll see you all in the next session. Enjoy the rest of your day, and please feel free to email me or text me in the LinkedIn. Happy to reply to your questions. See you next time, and bye for now.